Hi, I'm Michael Bisbano, and today I'll be presenting the results of my course project. What is sonar bathymetry? Bathymetry is a real fancy word, but it really just means the mapping of underwater depths, much like topographical maps are made for things on land. This picture here on the left is an example of a waterway being mapped with bathymetry. There are many applications of bathymetry, but some common ones are scanning foundations for oceanic wind farms to make sure there isn't any damage, or if there is damage, to do repairs. It can also be used for charting maps for shipping lanes and channels, search and rescue missions, and mine and explosive detection. How does it work? So a fish is towed through the water, and a mounted transducer will transmit a strong acoustic narrowband pulse. That pulse will propagate outwards, reflect off the seabed, and some of that energy will return to the fish, where a receive transducer element array will be able to calculate the direction of arrival of that received signal due to the phase differences on the different elements. And also the range of that return is encoded in the time of the response. So range is equal to half of the two-way travel time times the speed of sound in the water. So by aggregating the range and the direction of arrival for a long series of samples, you can actually generate a 3D image of the bottom profile, like we were seeing here before. So my goal for the project is to make an intuitive 2D visualization and animation of the sonar bathymetry direction of arrival problem. So I'd like to animate a sound wave propagating out from the fish, scattering off the bottom, and returning to the fish to make the premise of bathymetry clear and intuitive for anyone watching it. So the goal is to have a completely configurable set of MATLAB scripts which can be run with different parameters for depth, bottom profile, and the position of a target. The purpose for this is my senior design project is implementing a direction of arrival algorithm in machine learning to see if it can improve on current algorithms. And when I discuss my senior design project with people outside of the field of engineering, I find people often struggle understanding just how we can use sound to map out the bottom of the ocean. It's not really intuitive to them. But, I mean, having said that, people do understand that with our two ears, we can determine what direction sound comes from. So it's possible for us to visualize this and animate it in a sense that helps people understand how bathymetry works, what's happening, some of the math involved in an intuitive sense, and how this can also be used in other applications. So since this is such a complicated acoustic environment, there are quite a few limitations I'm going to have to set on the scope of the project just to make sure I can get it done in time and also accomplish it on my personal computer. So for one, I'll only be showing a 2D slice of the pressure waves traveling underwater. This makes my life a little bit easier for sure, and I think it will also make the concept easier to understand and less overwhelming to observe. So the animation will be displayed in the depth and across track range plane. And the across track range is just the distance along the bottom perpendicular to the direction of travel of the fish. Now, another limitation is I break up the bottom surface into a discrete set of reflection points. In real life, the entire bottom surface will reflect the transmitted pulse, but simulating that will quickly become too intensive for a computer to handle quickly. So I've decided to set a configurable amount of reflection points along the bottom so that a user can specify just how cluttered they want their animation to be, and also determine how long they want their animation to take to render. If they increase the amount of discrete reflection points, it'll be a more realistic approximation of the environment, but it'll be much more cluttered looking and harder for them to really follow what's happening. Next, I'm also going to have to approximate the transmitter and the spherical the reflection points as spherical sources. In real life, the transmit element has some directionality, and there are really many factors that determine the reflection points properties and directionality. But by approximating both of those as spherical sources, it makes my calculations much simpler, and it also makes viewing the animation more intuitive and simpler to follow. The final limitation of my project is I'm setting the water columns properties as a static constant. The speed of sound in this simulation is not a function of depth. In real life, people working in bathymetry problems will record the speed of sound as a function of depth in their environment before they start making measurements, and then they can use that to counteract the skewing or the bending of sound underwater due to the change in temperature, salinity, and pressure. You can also measure the temperature, salinity, and pressure and calculate the speed of sound using Del Grosso's equation shown here. But for this project, since bathymetry is generally done in such shallow water, for a simple animation like this, the speed of sound's variance isn't that important, and I'll be setting it to just a constant 1500 meters per second. Now we're going to get into how my code works. I basically define a number of pixels on the screen that I would like to use to represent the underwater environment. I've been setting that to 1280 by 720 for now, just to follow a sort of standard. I then generate a 3-dimensional array with those dimensions, and the third dimension being an index between different values and parameters set for each of those pixels. I call this array the MAR or master array, which is a very memory intensive way of solving this problem, but it lets me use the find function built into MATLAB to find certain pixels that meet specific criteria pretty easily. So again, I can index in the master array by the Z or depth index, the X or crosstalk range index for the pixels, and then the value index for what value I want to pull out of that pixel. And here are some of the elements in the master array. So elements 1 and 2 contain the X and Z values of a given pixel. And then those are used to calculate element 3, which is the radius from the origin, where the TX transducer lies. Element 4 is just a Boolean array set to 1 for any pixel positioned above the bottom. And element 5, much like that, is a Boolean array, which is set to 1 for any pixel that is positioned below the bottom or inside of the target rectangle. So those are set for anything that can cause a collision. Element 6 is just the angle between the given pixel I'm looking at and the origin. And element 7 is just a Boolean array, which contains a 1 when a pixel is in the collision matrix and is hit with a raycast from the origin. So that's basically a reflective surface mapped from the origin. Some of the most important ones here are element 8 and then elements 9 and on. Element 8 is a Boolean array with pixels set to 1 when they are in a region of acoustic or sound shadow from the transmit pulse. So if the target is blocking a region from being hit by the transmitted pulse, then that region that is blocked will be filled with 1s in my master array, which lets the code know not to plot the transmitted wave there. And then elements 9 and on are basically all of these important values here, like the radius, the angle, and the shadow array for all of the discrete reflection points I configure in the code. So the length of elements 9 and on, or the length of the total master array, depends on how many reflection points I have set. So actually generating and filling in all the values for the master array takes a pretty big chunk of time, and it takes even longer the more reflection points I render. To determine the reflection points, I use that element 7 of the master array, which is the reflective surfaces, which I make using a raycasting technique. I look for the first reflective object hit from the origin at each angle I index along, and then taking all of those elements on the reflective surfaces, I try to evenly distribute the set number of reflection points along those surfaces so that we get a good approximation of what the bottom looks like, even though we're only using a minimum number of reflection points. And then the wave is actually animated by making a time sequence from 0 to the max two-way travel time, which would be the max range multiplied by time or speed of sound. So we take that, and for each time sample in between 0 and the max two-way travel time, we find all the pixels that aren't shadowed that are at the correct radius for the given frequency and wave number. So for all pixels where there's no shadow cast and the radius falls in the possible range from the source, a scatter plot is made and all of those pixels are plotted. And we repeat that for both the transmitted wave and then every single one of the reflection points. Because this has to repeat for every time sample, there are some nested for loops there, and that makes it take a very long time to actually render. So watching it in real time while it's playing is pretty boring, but using the getFrame function in MATLAB, you can capture all of these frames and then play it back later in full speed. And that's what I've done here. So here I'm going to move over to a demonstration. So here I've made a little code which I'll be sharing with everyone. I've recorded map files for all of the different simulations I've done for different numbers of reflection points. But here I can, if I run this here, you can't see it, but on another screen I've opened up a figure, and now I can load in, let's say, just a surface with no target, and let's do 12 reflection points. So I'm going to load that in. And now I can scroll down and actually play that movie. But before I play it, I'm going to switch screens so you can see the figure. So now I'm going to play it. And you can see in red, the transmitted pulse travels out, bounces off the bottom, and reflected waves travel back. On this screen, you see my mouse right here. These blue diamonds are the discrete reflection points I've drawn out along the surface. Up here, the red diamond is the transmit element, and the blue circles represent where in physical space the receive elements would be. Obviously, when we animated that, the blue waves traveling back are the reflected waves, and the red wave traveling out is the transmitted wave front. And down here in the bottom right, buried below the surface, is the target. I placed it there just so we only have to worry about the surface for this example. But I'll play it one more time so you can see the wave traveling out. You see it propagates, reflects here, and comes out. And you can see the normal angle to these wavefronts as they cross here is what a direction of arrival approximation algorithm would infer as the direction of arrival. So the first wavefront that comes back, it infers as coming from almost straight below, and the last one, it infers as coming from out here. If I switch back over here, let me load a small target in. Or actually, first, let's look at if I take more reflection points. So this is going to be 50 reflection points along the bottom instead of just 12. This gets a little bit more hectic, but you can see it's probably a more realistic representation of what the bottom looks like. You can see the direction of arrival is changing. It's turning out more this way as opposed to coming from straight down in the beginning. I'll play that one more time so you can see. And I found that I recorded all the way from 6 reflection points to 100 reflection points for each of these configurations with the target and the bottom mapped. And I found that 100 is too much and 6 is too few to see what's going on. So 12 to 25 to 50 is a good sweet spot for representing how the waves propagate. Now I'm gonna switch over here and let's load up a small target with 12 reflection points. So this small target, that black rectangle you saw before, is going to be moved out above the surface, and we'll actually be able to see waves reflecting off of that when I play it here. So you can see the target is actually moved out. And these waves propagate along. You can see the normal angle as they're traveling across their transmit. This transmit element would be the direction of arrival they came from. Now, as I increase to more reflection points, let's go up to 50. And play that again. I'll play it a little slower so you can see it better. This is 20 frames a second. As this goes out, we're going to start to get multipath response between these elements. So the received signal, when it's coming back there, it's going to be pretty inconclusive. You can see this is a jumbled mess. So it's a good representation of how when you have a non-continuous or flat bottom, your signals back are going to be more confusing to interpret as a direction of arrival algorithm. So things get much more complicated in a more tumultuous bottom shape. If I switch to a large target on the bottom with 25 reflection points, and I run this, put it back to 40 frames a second, you can see here the inferred direction of arrival with only 25 points. You can still see the direction of arrival for each wave traveling back, but you can imagine as the limit of reflection points approaches infinity, like real life, that gets very noisy and hard to infer. And then the last thing I'd like to show is if we load in a vertical wall or cliff on the side over here as a target. This is an interesting example because it shows that as these waves travel back, now this wavefront is actually bouncing back down. So we had the received signal was originally coming from this direction, and then it jumps up to here because this is closer than these. So the received direction comes from here, and then it travels back down in this direction. And we get multipath here, and that's confusing. But for the scope of my senior design project, we're only working on a relatively flat bottom. So the direction of arrival will continuously be increasing upwards and outwards. But you can imagine in real life, you don't know what's going to be there. So you can't just assume that the bottom will be relatively flat. And if you do, you could run into issues where you're inaccurately determining the direction of arrival. But now to switch back to the PowerPoint real quick, I'm going to go over some things I would improve on if I were to continue doing this in the future. First, I'd like to optimize the code. Currently, it's way too inefficient to run real time. It takes like an hour to render, especially with 100 reflection points. I think if I use some techniques from video game design for ray tracing and whatnot and rendering graphics, I could optimize this to run on less powerful hardware without significant processing delay. And if I migrate to a better software solution, like processing, which is a subset of JavaScript, there are some software options that provide more native support for using your GPU and And processing, for example, is basically tailored for making scientific simulations. So I think spending the time to learn that and use that instead of MATLAB might make developing this code a little bit better in the long run. The other thing I would want to do is improve. You could see there are a few visual errors in the shadow casting I developed, which is just from a small bug I couldn't figure out in the ray casting code. If I spent more time to sort that out, it would be a more visually accurate representation of the acoustic environment, and it would make a few better animations of it. For now, it takes so long to run, and it's very computationally intensive. So people interested in the results generated by this code are probably going to have to reference the video recordings I made on YouTube, because running it themselves is really not feasible. I have 64 gigabytes of RAM and I was flatlined. So in the future, if I made this better, I think it would be a really useful teaching aid for showing, multipath and applications of sonar in real life.